So what does it mean to actually solve an equation? Well, first things, let's decide or discuss what an equation actually is. If you can see, that word starts with the letters EQUA, which is most of another word that we're all familiar with, the word equals. So an equation is a mathematical expression that has an equal sign in it, just like this one here. Now, 3 equals 3 is a real basic equation, and we all agree that that's true. Like 3 does equal 3, so we would say that equation is true. What about this one though? 2 equals 3. Well, it's an equation, but it's clearly not true. 2 does not equal 3, so we would say that equation is not true. So what does it mean to solve an equation? Now, you might remember, you might have heard the word solve in like solve a mystery or solve a puzzle. There's something that's unknown, and by solving it, you figure out what the unknown is. And that's just like what we do in algebra. Remember, we use letters like this one here, this X, to represent things that are unknown, numbers we don't know. So we replace them or substitute them with a letter. Now, in this case, I've got an equation, x plus 2 equals 3. To solve it, I have to find the value for x that makes the equation true. That will be its solution. If I can find the value for x in this case, or the unknown, to make it true, that is how I solve it. And this one's nice and easy. Let's lay it out in front of us, and you can just look at that one and figure it out. And we call this technique observation, and it's a legitimate technique. If you can solve an equation through just looking at it and going, oh yeah, it has to be blah, then using observation is fine. Go for it. Okay, so I can look at that and go, well, something plus 2 has to equal 3. That must be 1, because 1 plus 2 equals 3, so my x has to be equal to 1. And we would say that the solution to that equation is x equals 1, because that's what makes it true. Okay, that technique was using observation. But sometimes they're a bit too hard to use observation. So we've got some other techniques. But first I want to just explain, before I show you this technique, just this idea of an equation, how it's got to stay in balance. Now we'll start with this one we talked about before, 3 equals 3. I can represent that equation kind of like a seesaw. And if you imagine the equal sign is the bit in the middle. And for the thing to be in balance, you have to have the same on both sides, which I've got here. I've got 3 equals 3. It's in balance. It's like a seesaw that's not tipping either way. What if I added 2 more to one side though? It would tip. It'd be too heavy on one side. To get it back into balance, if I added 2 on the left hand side, to get it back into balance, I'd have to add another 2 on the right hand side. Now I've got my equation back in balance. It's true again. 5 equals 5. And this idea of adding one thing to one side and to the other is really critical. Because you can do whatever you want to an equation, so long as you do the same thing to both sides. And we're going to do some examples of that right now, because it's really important you get your head around that. You can do it whatever you want, but whatever you do to one side, you have to do the other side, just like getting that seesaw back into balance. Here's our equation from the previous question. We know that the answer is going to be x equals 1, because we already answered that back down here. But let's go through and use this idea of balance and doing things to each side to keep it in balance. The next important thing I want to get your head around is that to get rid of numbers, we do the opposite. And let me give you an example. To get this solution looking like x equals something, I have to get rid of this stuff that's on the same side as the x. I have to get rid of a plus 2. What's the opposite of plus 2? Minus 2. I get rid of it by doing the opposite. If I've got a plus 2, I can take 2 from it to get rid of it. I've got 2 things here, I take them away and they're gone, right? That's the idea. But remember, we said whatever we do to one side, we have to do to the other. So if I'm going to take 2 from the left-hand side, I have to take 2 from the right-hand side to keep it in balance, like a seesaw. The reason I would do that is that these 2 here basically write each other off. They cancel each other out. They're what we call a zero pair, because when I add plus 2 and minus 2, I get 0. Nothing. It's gone. That's exactly what I wanted. I wanted to get rid of it. And I did that by doing the opposite. So now on the left-hand side, all I've got is x. On the right-hand side, I've got 3 minus 2. So x equals 1, which is great because that's the same answer that we had back here for our first solution. So good sign. Let's apply that idea to something that's got some little bit uglier numbers. You might be able to do this by observation. Just look at it and go, oh, well, yeah, it's blah. But some ugly numbers there. So let's apply this idea of getting rid of something and doing the same to both sides. I want to get rid of this minus 17 because I want the x on its own. So what's the opposite of minus 17? Well, it's plus 17. So I'm going to get rid of it by doing the opposite. Whatever I do to one side, I have to do to the other. So now that becomes a zero pair. It's gone. It disappears basically. So on the left-hand side, I've got x. On the right-hand side, when I add these two together, I get an answer of x equals 448. We solved it. The value for x was 448. Well, that's great for pluses and minuses, but what about if we're doing times and divide? Now, hopefully you remember that those two operations, timesing, multiplying, and dividing, are opposites. So that's going to come in real handy. Here's an equation. X over 3 equals 9. Now remember, fraction just means divide. So basically what's happening here is x divided by 3 equals 9. To solve it, I want to get an answer that says x equals something. What value for x makes this true? Now you might be able to do that by observation because something divided by 3 gives me 9. You can probably see the answer is going to be 27, but let's go through and do it step by step just in case you couldn't do that one by observation. What is the opposite of dividing something by 3? Well, the opposite of dividing by 3 is multiplying by 3. So I'm going to multiply both sides by 3. Now, because this is a fraction, I'm going to put the bracket around the whole thing just to remind me that I'm multiplying the entire left-hand side. And I'm multiplying it by 3. And hopefully you remember from previous algebra, we can just put a number outside of brackets means 3 times whatever's in the bracket. So I'm going to do the same to the other side. So I'm multiplying this side by 3, and I'm multiplying this side by 3. Now, hopefully you can see I've got common factors that I can cancel out here. 3 on the top and a 3 on the bottom. I can cancel them out, which leaves me with just my x. Perfect, that's what I was trying to do. So I've got x on the left-hand side. I've got 3 times 9 on the right-hand side. So my solution is x equals 27. I multiplied by 3 because that was the opposite of dividing by 3. One last example. What if I started with multiplication? 4x equals 20. 4x means 4 times x. They're being multiplied together. We just don't put the multiplication sign in. So I've got x times 4. The opposite of timesing something by 4 is dividing it by 4. So I'm going to write that out and divide the left-hand side by 4, but I have to do the same on the other side as well. So I'm dividing both sides by 4, and just like we had in the previous example, I've now got a common factor of 4 on the top and bottom that I can cancel out, which just leaves me with the x on the left-hand side. 20 divided by 4 is 5. So we've now got a solution. The solution to make that true was x equals 5. All right, that was a quick run through of just this idea of making solving an equation just means find the unknown value that makes it true, and we can apply that idea of doing the opposite to get rid of things so that we can whittle things down to our final answer where we've got our unknown. Great job, well done.